All right, hello again. We are going to continue talking about trends in the periodic table. We'll quickly review, though, about how the atomic radius changes and why it changes. And remember, for this chapter, you really need to be explained why, not just the trend, but tell me why that trend occurs. So the atomic radius, as we go across in the period, it goes from larger to smaller as we approach the noble gases. And the reason is the effective nuclear charge, the protons that are in the middle, want to pull those electrons in tighter and tighter and tighter, pulling them in closer. So we're going to find out that that makes it harder to steal or take away electrons in the outermost shell later on. The atomic radius, if we start at the top of a family, it gets bigger and bigger and bigger as we go down because we are adding more levels and that effective nuclear charge isn't as strong. Those protons aren't able to grab those electrons in the outermost shell and pull them closer anymore. It keeps expanding because we're adding more levels in, and that nuclear charge between the protons and those electrons in the outermost shell is not as strong. So let's move on to today's new information. And if we look, what we want to be able to do today is talk about what happens to the ion as an atom gains or loses electrons. How does that radius change because we've either added an electron or taken a ones away from that outermost shell? The atoms that gain, the negative ones, they become larger. So if I have chlorine and it looks like this, and I put another electron in, we're going to find that the ion radius is larger. And the reason that is that if you've ever taken a magnet and you try to push the two negative ends and they repel each other, it's going to cause the same thing happens with electrons. We're trying to put an extra electron into this outermost shell. Remember, these electrons are flying around, they're moving. And so when you try to put another one in with negative ion, it gains an electron. Those electrons repel each other. They don't want to fly next to each other. So there's electrostatic repulsion, and that causes the ion to swell. So let's think about a positive ion. Here, I've got a positive ion, and this time, for it to become positive, I'm going to take electrons away. What do you think is going to happen? Well, they become smaller. So here is sodium. I pull away an electron from it, and that new ion radius is going to get smaller, and it's for two reasons. One, we now have an empty shell. We don't have that S subshell anymore, so it's empty, which causes it to be smaller. And we have less electrostatic repulsion, allowing these electrons to fly closer together. So those are the two things that happen with that. Ionization energy is the energy required to move an electron from a gaseous atom. So basically, it's how much energy does it take for like sodium to pull an electron away from it versus chlorine. You can pull an electron away even from a noble gas, but it should make sense that if it has 8 in its outermost shell like neon, it's not going to want to give any of those up. And also remember, neon has a small radius, so it's those protons in the middle are going to really hold on to those electrons. They don't want to give them up. So that ionization indicates how strongly an atom has hold of those valence electrons. And it should make sense that the smaller the radius, the more pull those protons have on it, and it's going to require more energy to steal them away. So the first one to pull away the first electron, for let's say calcium, has a first ionization energy, and it also has a second because you have to pull away 2 electrons in calcium. So it has a second ionization energy. They went on a huge limb giving it those fancy names of first ionization energy and a second ionization energy. and it gets excessive. You could pull away all the electrons for calcium in a lab, but that's not going to happen in nature. So the ionization energy is dependent upon the size. So as the radius gets smaller, that ionization energy is going to increase. As the radius gets bigger, it's easier to steal these electrons in the outermost shell away, and you can see that the ionization energy is going to get decrease. So you have those notes there to read through and explain that. I'll let you read about electronegativity. We're not going to spend too much time on that one, nearly as much. And then notice on the rest of this chapter, I have review on the key concepts we have that you need to know. And what I want to talk about now is the homework you have for today. You have a worksheet, and we're going to practice doing AP level questions. Now, you might take AP chemistry in the future, or you might take AP biology. Most of you, that would be your next step, is to go take AP. And AP is a college prep class where if you pass the AP test at the end of the year, you get college credits already. So you would, if you took AP biology, you would go into your freshman year of college already with those credits in there. And what you do is you take a national test to see if you pass it. And if you get a 3 or a 4 or a 5 on that test, you get the college credit. There are 5 points total on an AP test, at least scoring overall. The way the tests are done is you get AP questions like this. And the big thing that you have to learn is to answer the questions completely. Yes, no, or just saying there's a trend is not enough. You need to explain why. So we're going to practice those a little bit today, and I was going to do a couple of them with you. So the first question is, a sample of natural selenium contains 6 stable isotopes. In terms of atomic structure, explain what these isotopes have in common and how they differ. So you can't just say isotopes have different masses. That's not quite enough in an AP type of question. So I'm going to share the correct answer with you of how it's done. So here, number 1, the 6 isotopes of selenium have the same number of protons. So we're saying right away that the protons don't change, but a different number of neutron causes different masses. So that right there, writing that out, would give you 1 point on this section of the test. If you just say an isotope has different masses, that's not enough. You have to explain why it has different masses, and the different mass is due to different number of neutrons. The second problem asks you to figure out how many unpaired electrons are there. Well, first of all, it said you had to write a complete electron configuration. Excuse me. So you cannot do the new shorthand we had. If it says complete, you need to show the complete electron configuration, which by doing that, I earn a point. And then I'm able to say, because I can show it, they can see it, that there are 2 unpaired electrons. And the reason for that is Hund's rule is each orbital in P has 3 before anybody else gets a second. So I showed the configuration. There's my 1 point. And then I get I get another point for saying there's 2 unpaired electrons, and I get a 3rd point for saying Hund's rule is the reason I have those unpaired electrons. So you have the answers to this worksheet. So I think it's just good practice, either if you take AP chemistry or AP biology, just to kind of get a feel of the type of questions that you have in these. So if you have any more questions, feel free to zoom back in and ask me any questions, but you should be able to work on the homework and practice understanding those trends.